Welcome. I'm Dr. Anitha, and in the next 30 minutes, I'm going to take you on a journey that connects classroom math with real world wonders. We are talking about bridges, water fountains, sport shots, even satellites in space, and the one mathematical curve that connects them all is the parabola. But here's what makes this exciting. It's not just about shapes, it's about strength, elegance, and engineering power. So let's dive in and discover why parabolas are everywhere and how this one curve is quietly shaping the world around us. See this bridge, the golden arcs of McDonald's? These aren't just beautiful shapes, they hide a powerful math secret. This secret is the parabola, a U-shaped curve that turns out to be one of the strongest, most versatile tools in science and engineering. And in this video, we are going to explore why and how. Let's travel back nearly 2000 years. The ancient Romans built massive stone structures, aqueducts, bridges, amphitheaters, using no steel and no modern cement. They relied on precisely cut stone, lime mortar, and most importantly, the curved arc. This design wasn't just beautiful, it was smart engineering. The arc shape distributes weight evenly and directs force into the ground, making structures incredibly stable, even without today's material. Now, contrast that with many flat modern structures. Without the right support or the right math, they can fail under the pressure. So, what made the Roman arc last for centuries while some modern beams don't? It's not magic, it's mathematics. More specifically, it's the geometry of the curves. And among those curves, the parabola stands out as one of the most powerful. Let's test your observation skills. You're looking at four different objects: a bridge, a circle on drawing on a paper, a water fountain, and a straight road. Take a moment and ask yourself which of these images show a parabola. Look closely at their curves and shapes. Go ahead. Let's see how you did. The correct answer is the bridge and the fountain. The bridge uses a parabolic arc not just for beauty but because it helps support weight evenly. The fountain spray follows a parabolic path caused by the physics of projectile motion and gravity. The circle, although a curved, is a closed shape, not a parabola, and the road is a straight line. There is no curvature at all. So parabolas are special because they are open, symmetrical, and shaped by the special equation y equal to ax squared plus bx plus c. We will be using this equation throughout the presentation to understand how engineers model curves in bridges, fountains, and more. Now that we have seen where parabolas appears in real life, let's understand what actually creates them. It's all come down to this simple equation y equal to ax squared plus bx plus c. This is called a quadratic equation and it's the foundation of every parabolic curve you will ever see. Let's break it down. What do these letters actually do? First, the letter A. It controls how wide or narrow the parabola is and whether it's open up or down. If A is positive, the parabola opens upward like a cup. If A is negative, it opens downward like a water fountain. The larger value of A makes the curve steeper, while a smaller value makes it wider. Think of A as the one that shapes the curve. Next is B. This moves the vertex or turning point left or right. It doesn't stretch or flip the curve, it just slides it sideways. Imagine B as shifting the whole curve's position on the x-axis. And finally, the C. This controls where the parabola crosses the y-axis. It lifts or drops the curve vertically. You can think of C like adjusting the whole graph up or down on the screen. So in summary, A controls the shape and direction, B shifts the curve left or right, C moves it up or down. So this one equation gives us control over the entire curve, and that exactly why it is so useful in engineering. This is a simple but powerful visual of the standard quadratic equation y equal to ax squared plus bx plus c. Right now we have set the a value is initially 0.1, b 0 and c also 0. The red curve you see is a parabola opening upwards. Let's explore what happens when we adjust these values using the sliders. When we change the value of A, the graph becomes narrower or wider. A small a like zero point 0.1 makes the parabola very wide, like a shallow ball. The larger a value, say 2 or 3, would make it sharper and more steep. If a is negative, the parabola flips downward. We can shift the graph left or right using B and move it up or down using C. This tool helps us to understand how each part of the equation affects the shape of the curve, making math interactive and visual. Here is something cool. Every time an athlete throws or kicks or shoots, they are creating a parabola. Take a basketball free throw, for example. Watch the arc of the shot. It's not just talent or muscle memory, it's pure math in motion. The shape of the curve depends on the angle of release, the initial speed, and s, the same equation we saw earlier, y equal to ax squared plus bx plus c. The values of A, B, and C determine how high the ball goes, how far it travels, and where it lands in the hoop or misses. And it's not just basketball, whether it's a javelin in athletics, a football kick, or even a long jump, every athlete is following a parabolic path shaped by the laws of physics and motion. The best part? Great athletes may not know the equation, but they are mastered the curve with training. Whether they realize it or not, they are using parabolas every single game. Now, let's turn to sports, and what better example than basketball? In this video taken from Kobe Bryant's farewell game, you can imagine the path of the ball isn't visible in midair here. We know from physics and experience that it follows a curved path. Every time a player shoots the ball, they are using the principles of projectile motion. The ball rises, slow down at the top, and then falls, forming a perfect U-shaped parabola. The success of the shot depends on the right angle, the speed, and height, all of which can be modeled using a quadratic equation. This shows us how math, especially parabolas, plays a major role in real life performance, even in world class sports. So, next time you can see a greater shot, remember there is a beautiful math curve behind that moment. Now let's switch gears and put you in the role of engineer. Imagine you have been given a challenge. Design a bridge arc that is not only strong but also safe and efficient. And here is your tool, not concrete or steel, but a simple quadratic equation: y equal to ax squared plus bx plus c. Now, now visually we are going to construct the bridge using the GeoGebra. So here, start with the shallow curve, something wide and flat, looks nice, but would it hold weight? Probably not. That might be too sharp, not ideal for traffic to pass over. This is the balance engineers have to strike every day. Too flat, it sags. Too steep, it's impractical. And amazingly, that entire shape and its strength is controlled by three numbers A, B, and C. Is it that powerful? This is where math meets real world design and gives us the power to build things that last. Hope you have understand this concept in this GeoGebra tool. Let's take a closer look at one of the most famous landmarks in the world, the Eiffel Tower. Most people admire its beauty, but few realize it's full of parabolic design. Gutzwey Eiffel wasn't just building tall, he was building smart by using parabolic curves In the iron framework, he distributed the force of wind and weight evenly, making the tower incredibly lightweight yet strong. This is a brilliant example of how geometry shapes engineering. Now, let's shoot beyond the Earth. Have you ever wondered why satellite dishes have that bowl like shape? It's no accident. That shape is actually a 3D parabola called the paraboloid. Here is the secret. A parabola has a special property. It can take in waves, even weak ones, and reflect them all to a single point called the focus. That's how we receive satellite signals from thousands of kilometers away. TV, GPS, internet, all thanks to parabolas silently working in the background. Whether it's Earth's tallest tower or communication with outer space, the parabolas are everywhere doing extraordinary things. Understanding parabola isn't just about building cool structures, it's also about avoiding engineering disasters. Let's start with something beautiful, a water fountain. Engineers use equation like y equal to minus x squared to design these fountains. So the fountain equation is y equal to minus x squared, where we are getting the downward arc. The negative sign is important. It flips the parabola downward just like the arc of the water. The shape of the fountain is not random. It's carefully calculated using math. The height and reach of every jet depend on adjusting just a few numbers in simple quadratic equation. In fact, let's model one live, see how we can control the arc using the tools like GeoGebra or Desmos in the next slide. Now let's switching to something more serious. What happens when we ignoring parabolic strength? Look at these two structures. One has a flat roof and another has the dome. So here the flat roof may look fine at first, but under the weight of snow, water, or high winds, it can collapse. In contrast, the dome, built with a parabolic curve, handles weight better. Its shape naturally channels forces outward and downward, keeping it strong and stable. So, from fountains to domes, the parabola isn't just a pretty curve, it's a powerful tool in engineering that helps us build stronger, smarter, and safe structures. Let's look at this beautiful image of a fountain, but it's time through the lens of the math. So you see the two water streams in different colors, both form a parabola, that smooth curve U shape we study in math. Each curve is made using a quadratic equation. The first one is f of x is minus 1.56x squared plus 8.56x plus 2.36. And the second one is g of x, which is given by minus 0.84x squared minus 6.91x minus zero point 0.4 at the initial. Now, what do these numbers mean? The first number called A controls how short or wide the curve is. The second number called B moves it sideways. The third number called C moves it up or down. So we can use the sliders to change this value and see how the water path changes. Just like an engineer does when designing a fountain, um, the water should land in the right place without splashing everywhere. So this shows how math is not just in books, it's in parks, fountains, buildings, and even water. So when students learn to change the shape using equations, they are actually learning how to design something real. Here we have another example of real life parabola created using the Desmos graphing tool, where the previous slides was done by using the GeoGebra. In the background, we see an image of real fountain, and over it, we have drawn a purple curve that perfectly matches the path of the water stream. This curved path is not random, it's a parabola, just like the one we studied in math. So using a Desmo slider on the left, we adjusted different values, A1, A2, A3, and so on, to fine tune the curve. These sliders help changing the shape, width, and position of the parabola until it fits the water path exactly. This is a great example of how we can use quadratic equations to model the real world motion. Whether it's a fountain, a ball thrown in the air, or water sprayed from a pipe, the path is always parabola. By experimenting with the sliders, students can see how changing a number slightly can make a big difference um, in where the water lands. This is how engineers use math in design. They test, adjust, and calculate to make sure the water falls exactly where it should. So it's a really interesting tool which helps us to visualize the abstract thing, and also we are doing it by ourselves. So what started as a simple curve, just y equal to ax squared plus bx plus c, has turned out to be one of the most powerful tools in science, design, and even everyday life. We have seen it in bridges that stand the test of time, fountains that dance in perfect arcs, sports where every shot is a curve of victory, and space where signals travel through perfectly focused path. So parabolas are everywhere, not just in textbooks, but in the world around us. So next time you cross a bridge, throw a ball, or even look at a satellite dish, remember you are seeing math in action. And as per the engineers, designers, and thinkers, this is the kind of math that gives you power to build, to create, to solve, to lead. Thank you for joining me in this math adventure. Keep exploring, keep questioning, and never underestimate the power of simple curve. Thank you.